So in enhanced graphics, we're going to be looking at three main sections. We're going to be looking at some new shaders for changing the appearance of elements in graphics. We're going to be looking at extensions and improvements to textures. So applying patterns or pictures or arbitrary content to surfaces and regions and whatnot. And then we'll also be looking at some new functionality for highlighting values in plots and exploring plots interactively. So now we'll go ahead and share, and we'll go ahead and do that. And so starting off with the extensions to the shaders. So we have three new shaders similar to some of the gradient shading and pattern filling type functionality. So the first is blurring, and it does what it says. So I have some text here inside of a graphic. So here's my text. Um, and I'm going to blur it. And so this is my graphic, and here is my text, and it is rendered in a blurred fashion. And the blurring radius in this case is 12 points wide. You can, of course, vary what the blurring radius is. Yeah, so if you set it to 0, it's going to look exactly like an unblurred thing, and then as you increase the blurring radius, it's going to get more and more blurry. And that one's fairly simple. And then the others are going to build in terms of that, in terms of complexity. So the second one that we want to talk about is drop shadowing. And this drop shadowing takes a copy of your element, whether it's a disk or a point or a line or in this case, text again, and it makes a copy in the background and moves it a little bit from the original. And so in this case, our copy is 10 points to the left and 10 points down from our original text. And by default, it's being rendered in a gray color instead of the style that was used for the text itself. And so it's sort of creating a shadow. And there's a lot of functionality here that you can customize. So you can change what direction you're going in. So this is going 10 to the left and 10 up. We're specifying a blurring radius of 10 so that it gets more of that shadow. It becomes more shadow-esque and becomes less of a focus when you're looking at a thing. And then we're also able to change the color for the shadow. So in this case, we're doing a blurred brown shadow of our text. And drop shadowing is kind of nice because it gives a feeling of being 3D, and that can be used to emphasize things or make it pop out at you a little bit more. So here we have a bunch of disks, and they just all have the same drop shadow. It's just the default, so it's 3 points down and 3 points to the left. Um, and you get that stacking effect um, that makes it have a little bit of depth to it. And you can use this in visualization functions or elsewhere. So here we're going to look at it in geographics. So here's a map of the world, and we've highlighted the United States and India in green. And that's it. I mean, we haven't used drop shadowing on this one yet. But the one below it, we have used drop shadowing, and it is a little bit of a blur. This is basically the default shadow direction. Um, and now that drop shadow brings those countries to the front a bit more. The green polygons haven't moved on screen, but that shadow helps to separate them from their background, um, and stand out a little bit more. And you get, I feel a little bit, sort of better distinction between the green and the blue on the ocean on the west coasts of those countries. Um, and so I think this is a very effective technique that can be used in places. The final shader we're going to look at is haloing. And what this does is it puts a border or halo around the elements. So here's our Wolfram text, and this is putting an orange border 3 points wide around it. Um, and again, this has a lot of flexibility. So we can control the thickness and the style. And so in this case, we have our orange border. I changed it to 4 points wide for just a straight border, similar to this one above that was 3. And then it has 4 points of blurring. And so you have your border, and then it will blur off past that. And if you're doing the blurring, you can also specify an alternate color for it. So I'm using orange and red. And so we have solid orange around Wolfram, and then we have a red that fades off as it blurs into the background. And so haloing is good for making things stand out against busy backgrounds because the halo cuts out everything around your object that might be going on behind it. And so here we have a list plot, and we've got some data. We've got one special data set that we're especially interested in. And I tried to emphasize it by making it red and making it a bit thicker. And it kind of works, but it's still getting lost in there a little bit. But if we add a halo to it, then that red line really pops out because nothing can get close to it. It's in front of everything, and it has that white buffer zone, that white border around it that knocks out everything behind it. And here we do a similar thing with a graph, and we apply haloing to the edge style. And before, where all of these lines run into each other at their intersection points, all the edges, here no edges appear to intersect because haloing causes one to always go in front of the other. And so you have, I think, a little, it can be a little bit easier to see what's going where in some of these cases because one line is continuous and one is, sort of pushed to the background. The other thing that's interesting with haloing that is a neat application is everything we showed so far had the halo on the outside of the element. You can also specify a negative radius or negative border size and push it to the inside of the element. And so here we have a map of the world, and we're coloring every country. And every country has its own, sort of light pastelish color. Um, but our haloing is a color and a lighter version of that color, and we're doing negative distances. And so we get, sort of a fade from the borders inward, which is nice in this application because if you tried to style the borders on the outside, they'd collide with each other because everything fits up tightly against one another. And so by filling to the inside, you get that effect, but you aren't causing the US and Canada, for example, to interact with each other in a bad way. Um, and so I really like this example. I stole it from the docs and modified it because it's one of my favorite examples of haloing, um, of doing this. And if you look at old maps, you frequently actually do see this type of effect where, for identification purposes, they wanted to color the countries, but they didn't want to color them solidly all the way through. So you'd have a color at the border, and then it would fill inside with a lighter color. The next thing we want to look at is improvements to textures. And so, ever since version 8 of the Wolfram language, you've been able to apply textures to polygons, but you had to use vertex texture coordinates. And this is sort of inconvenient because if you have a polygon, with a bunch of vertices, then you had to say what how those vertices mapped into the texture, and that meant that you had to have vertices, among other things. And so we've tackled that on two fronts. One is we've added texture mapping with a bunch of named mappings that say, given a texture, how do I map it onto a surface? Um, am I projecting, from the faces of a cube? Am I essentially wrapping a cylinder around it? Am I wrapping a ball around it? Am I putting the surface on the top and just pushing, all the ink down, so to speak? And so that means that you don't have to manually specify what the mapping is on a per vertex basis. It also means that we can apply textures to primitives that don't really have vertices, like spheres and balls and toruses and those sorts of things. And so here um, we have a texture, we have a torus, and it just works. It has picked an automatic method based on that shape of what it thinks the best method is. Um, Here it is, but right, but we can do it on. Yes, here we're switching to sphere, but we can control what the mapping is. So here it's a cylindrical version, and we've got this texture, and we'll make it a little bit bigger. So it's a colored checkerboard with a black border. Um, and we can see that we have our sphere, and the black cap is coming from this edge at the top. If we use a different mapping, in this case box, then we've got basically 6 copies of this texture on each of these box faces, and those are pushing in on the sphere. And you can sort of see, here's one texture, or here's part of one texture on the right side, here's one on the top, here's one on the front. Um, if we map around, here's another one on the left, etc. And then finally, here we have planar. I guess maybe not finally, but we have planar. And so we have this, and it's pushing everything down. And so we get our little black borders at the far ends of the um, sphere in the XY plane. And you see, sort of where it's very vertical, we get long stripes of that texture because it's all coming from above. Spherical is wrapping it around better than I could ever do with a ball-shaped Christmas present. And we get a little bit of accumulation of the black border from the texture at the top and over on the back side. Now, it's also possible to specify the mapping as a second argument of texture. So if you've got a bunch of things in your scene, a bunch of objects, and you don't want to specify texture mapping for every object, but you want them all to have the same, say spherical mapping, then you can put it in the argument of texture here directly. And then these objects will all use that mapping to apply the texture to themselves. And so that's the improvements to texture. And finally, we'll look at the interactive highlighting that we added in version 13.3. And so this is done in a couple of ways. The most common is plot highlighting, which is a new option that controls the appearance or presence of interactive highlighting elements on plots. And so at the moment, it's pretty much turned on for things that generate points or curves in 2D. And so we have a plot here, And as I bring my mouse pointer over the curve, then I get a dynamic call out that tells me what the coordinates approximately are of that point. So, and as I move around, it follows that. If I move too far away from the curve, then it goes away. And here we have it for list plot. And so when I get to a point, I can see that this is, I guess, absolute boiling point of 5,285, probably Kelvin, maybe Celsius, probably Celsius actually. It's not including the units here. And the vaporization heat is 630. The highlighting follows the plot style. So up here they were all blue. Um, if I have multiple curves in a plot and they're all different styles, when I mouse over the green curve, the call out is colored green. Over the yellow curve, it has yellow colors, etc. There are lots of different effects that you can use for your highlighting. Um, this is a table taken from the documentation, and I think I trimmed it down a bit. Um, So you can specify just a pure style. So I can say that I want my plot highlighting to be red and thick. And so now when I mouse over it, it's red and thick. And in this case, I turned all the other plots into a gray so that the red one will stand out nicely. You can add drop lines. So if you say plot highlighting goes to drop line, when you mouse over, you'll get the call out as before, but you'll also get those two lines that go down to your axes. Um, and so as you move around, that will sort of follow. And again, if you get too far away, then the highlighting goes away. There are a couple of slice um, types of highlighting effects. And so these are good for multiple data sets, or if you have um, multiple values that might get you want to highlight within a line. And so here we have our X slice, and so it's slicing at a particular X value, following the X value of the cursor. And as I move around, it's giving me that line and showing me the intersection with each of those curves and giving me a call out for each of those curves. So I can see, okay, that's 8, 14, and 21. In this case, those are the accumulated values. Um, so those are what correspond over to the values on the y-axis. If you don't want the highlighting in a particular application, so you're creating a plot and using it in something else, and you don't want the highlighting to be a distraction, you can turn it off with highlighting none. And now this is just a plain graphic, and it doesn't do anything. And there are also cases where highlighting is turned off by default. And so, for example, if you have tooltips or your plot already has callouts, or there's perhaps other interactive behaviors, by default the highlighting will be turned off. And that's because in the case of, like, say, tooltip, when you mouse over the curve, the tooltip's going to fire. The highlighting would try to fire. One of them would win, one of them would lose. Occasionally both of them would succeed, and then it looks really weird. And so for generally having a good experience, if there's going to be confusion or a potentially bad interaction, we turn off the highlighting by default. You can also use the highlighted wrapper, which has been extended um, to support plot highlighting. And so in this case, we're going to highlight our first data set with the default ball type of effect, but the other two aren't. And because this is highlighted, that automatic turning off that we were discussing earlier is going to apply to the other two curves. And so the green curve doesn't react, the yellow curve doesn't react, the blue curve has the normal highlight. And so that may be useful in times when you have, like, one main curve, but you have, say, a curve above and below it that are less important, and you don't want them to be highlighted in the same way. You can also do static highlighting via placed, either with the option or with the highlighted wrapper. And so here we're going to say that we have an X slice highlight at X equals 7. And so at X equals 7, we have what you would have seen if you had done it interactively, but it's there permanently. It's just part of the graphic. And so this is good for if you want to do something for publication or mail something to a friend, and make sure that they're seeing what you're seeing. You can do a static highlight, and you don't need to provide the full coordinates. And so, here, we didn't say what the y values of 7 were. Even in the case where we only have one curve, you don't have to say that this is 13 comma 6.2 or whatever. It will um, pick that value on its own. And if you specify a coordinate that isn't on the curve, in this case, it's going to adjust it to be close to the curve. And so we said 8 comma 10. That would be up here. It's not on the curve. And so we pick the closest point that we can find and place it there. And this is, sort of an extreme example, but it means that, if I wanted to label this one, I could say, okay, that's about 14.5 and 15, and I could put those in here, and it would label, it would put it would highlight this point, and I wouldn't have to have it out to 16 decimal places or whatever to be exactly 14.5 and sine of 14.5 times 14.5 or whatever. And the highlighting is customizable, so you can combine highlight effects, so X line and Y label. And so these are, component highlights. These are components of highlights. And so we have a line at the X value that follows the X cursor, and we're showing what the Y value is at those points. And so this is how, for example, something like X slice might be constructed. And within that, I can change the styles of things. So I'm going to make my line be red. I'm going to let the label also use a red callout style, and I'm going to change the appearance of the callout. And so now when I mouse over, I have that red bit, drawing extra attention, and I've changed the appearance of the callout to something that just sort of shows the corners around the elements, rather than showing a full border. And so that concludes the main part of the talk. I'm going to look at the questions a little bit. And let's see. So, can you increase the callout font size? Yes. So, for example, let me. There's a couple of ways you can do it. So, when you're doing the, say building things up by components, and you have these, this association for the labels. So this takes all of the um, options of call out. And so I can say label style goes to 16, say. And now I have much bigger labels in that. The question then is, and I don't remember this off the top of my head, so I'm living by, playing with fire. So if we pick like this one, so we have drop line, and if we set, say, the label style generally for the graphic, so that changed the axis label style, but it also changes that style in the callouts. So it is possible to change the label style depending on how you want to change it and what else you want to change. It may have to be done at sort of a lower level like I did in the first one, or you may be able to just use label style globally for the graphic. So why the texturing in the torus was not complete. So let's look at that. And the quick answer, maybe I don't know. But let's see what it looks like. So in this case, we have, for this torus, we have 4 copies of this texture being applied to it. And so we have the yellows being, so it's starting here along the left edge, and then it's wrapping around the inside and coming out on the bottom at this magenta. And so the whole texture is being used in this case. In fact, 4 copies of it are being used. How the automatic one determined that, I'm not sure. I wasn't detailed. I was aware of the functionality from a high level, but not all the nitty gritty detail, all the nitty gritty implementation details. So it may be that depending on what you're doing, you want to specify a particular mapping or something. So if we redo this with, say, cylindrical, then we get a different appearance than we did before. And then sometimes it may require a little bit of experimentation to sort of get the mapping that you want. So maybe you wanted spherical for a torus, which I guess this is what I used at the bottom of this notebook, where I was doing the sphere and the torus both in spherical. And so in this case, how this gets mapped depends on the torus. It probably also depends somewhat on the sphere, so that like the blue sectors are lining up and whatnot. But you aren't necessarily going to get the entire texture represented over the entire surface. Or as we saw with the torus a moment ago, you may get multiple copies, or you may get, as in this case, multiple copies of part of the texture, because when it maps on, for this box, it's mapping in from the right, it's mapping in from the front, and there's an intersection point, and so they sort of interfere with each other and creates a cut that maps onto the surface. So I think that concludes my part of the presentation. I'll stick around for a few more minutes and answer any questions in chat that may come up for a little bit longer. But thank you. And now we'll go to Marcus, who will be talking about image, audio, and video computation.
Hello and welcome to the second part of today's talk about what's new in Mathematica version 14. The second part today will be about image, audio, and video computation. And as such, the outline should be of no surprise. We are talking about images, video, and audio. In particular, we're talking about OCR for images, the detection and recognition of a text. Then the second part will be about new developments in segmentation. And then eventually, just for the fun of it, we'll talk about image synthesis. And as an opposite or inverse operation, we're talking about image captions. Then the second part about video is about video creation, about video editing, new commands there, and a little bonus here about video rendering, because as you may have already learned in the first part, you can project textures onto a more 3D objects now, and that is not only true for images as textures, but for video as well. And last but not least, we turn to audio. There again, speech. So speech to text conversion, and then the opposite, the inverse operation is speech synthesis, turning text into speech. And last but not least, we're talking about 2 audio effects that have been greatly improved in Mathematica 14. Okay, images, and in particular OCR. OCR is a difficult subject, and as you may know, it not always works the way it is supposed to be. So we're glad to have some significant improvement now by incorporating what's called DBNet. DBNet relates to this article from 2019 by two Chinese universities in Wuhan and in Shanghai. The topic here is real-time scene detection with differential binarization, and DB refers to differential binarization. So please be my guest and read the article if you want to have more detail. For that, unfortunately, there is no time today. So I'm left with presenting you with the benefits that we reap in via this DBNet. So find text takes an image, and the default behavior is to find just the block of text in that image. In this case, it's given by a parallelogram. And this parallelogram I can then superimpose on the image to see where the text is located. If you want to have a more fine-grained resolution of this detection, you can ask for lines or words or even characters. In this particular case, I will ask for words, and here then I get 1, 2, 3, 4, 5, 6, 7, 8, 9 building blocks that make up this collection of words. And not only can you just get the regions of interest, but you can also ask for an aligned image and extraction of that region of interest. You can ask for bounding boxes. You can ask for the strength of the detection and for the angle of alignment. And here I just display this result as a database. And here you can see all the 9 words with the region of interest, high probability of detection, and their alignment corresponding to the horizontal. Just one more example in that direction. Here is a sticker on a lamp post somewhere in a city, and you can see there are letters the right way around, but also upside down. And so just as a proof of concept, here you can just see that find image text can also read letters, or for that matter, words that are upside down, in the case here, less and fear. And on top of it, you can even read here if you want to, or if you're capable, that is, with a given resolution, very small text, fine print that may be hard to recognize. All right, so once you have found your text, especially in large images, you can read it. And that can be rather beneficial if you're in the business of, for example, reading license plates that usually make up just a small part of a given image, as in this case. So if I run text recognize, you can automatically get here the license plate number without having to zoom in and extracting the license plate as such. And that is done by, as I said, DBNet to recognize, and then the actual recognition by default is done by our own trained network, Wolfram OCR version 1. Another example, sign of this is essentially a road sign for a municipal area in Germany, in case though here it has been overwritten by new skill and training. Default detection method is DBNet. Recognition method, as I said, is Wolfram OCR version 1. This gives you the result. Beforehand, it was all handled by Tesseract, and in this particular case, it gives you the same result. One more example, because there are always small issues you run into when you do OCR, especially doing it in the wild. The major obstacle is always that the text is, the OCR gets hampered by nearby features in this image, like here, street sign in Paris, much more fancy than the one previously. Anyway, what you have to try to get into your OCR is a decent padding. That means you want to get unobstructive surroundings around the text so that OCR can work well. This is not always possible. I mean, you can work here with find image text and padding size, but as you can see, with a padding size of 12, for example, you already have some other text and image features in the way. So what I do here is I just reduce this to padding size 2 and then do an image padding that does not relate to the image content here, but just as a fixed padding. If I do that and then run this through text recognize, then I get the reading here perfectly, Place du Canada. Okay, so much for OCR. Another recognition feature that we already had since version 13.3, but that was never really advertised, is shape detection and shape recognition. Now, this is a little bit more complicated than just OCR because shapes come in different sizes, orientations, and so forth. And these sizes and orientations, these parameters, should be also read out and should be detected via regression. So you already know that we do detect lines via half transforms, but this is a different approach. Here we have a parking lot again to, well, outline the features I'm interested in. I'll do a rich detect, so essentially a line detection on the image, do an image adjust, and now I have here all the markings on the parking lot, which I can try to find via now find image shapes and looking for line segments. And as you can see here, it does a really good job. But lines are just the old game in town. The new game in town is also to detect circles or ellipses. So, for example, with this eye, I can try to find the inner and outer boundary of the iris. So the inner one would be the boundary of the pupil. In both cases, I assume these to be circles in this particular case. So I can do an edge detect again, just to detect the edges. I have to choose a reasonable scale. If I take that's too small, I get all kinds of small features. If I take it too large, the lines will not be well positioned. So sweet spot in this case is a scale of 6 pixels. And then I can run find image shapes looking for circles. And in order not to find too many circles, I just go for those ones that are largest with respect to the region measure for 2D object. Well, actually, it's a 1D object. I'm looking for circles, not a disk. It's a circumference. And just the two largest circles with respect to circumference are given here and superimposed. And voila, I have an iris detector, so to say. One more example. The next more general case is an ellipse. So these wheels here, due to the angle of the viewpoint, are essentially ellipses. So I can just do the very same game. I do an edge detect, and then I'm trying to detect ellipses in this image, the 10 biggest one. And here are the results. You can see 1, 2, 3, 4. I basically captured all 5 wheels except for the last one here, which is a little bit covered too much behind other gear. And instead, I detected a smaller ellipse that was created due to a segment that ran from here to here, and where in principle you can see ellipse. There are lots of thresholds you can play with. Of course, here the threshold would be how much of the ellipse is actually visible. We try to get away with roughly a quadrant of an ellipse to detect ellipse. All right. Now, regarding detection and recognition, when we basically recognized objects in an image, so far we did this usually with CNNs, so-called convolutional neural networks, that essentially worked pretty much like a filter bank. You had little filters, local filters that you would extract from an image. Then basically for every position in the image you basically get the filter response. That is then a new feature, and on these features you run another filter and so forth until you stack up a fairly deep network. And these networks basically were first looking local and then obtained a larger and larger field of receptive field for every filter, essentially. Now, that problem is there's a problem, essentially, and that is that you can do a very simple experiment with your own vision. For example, in this case, you just see 3 V's, and they can be aligned in different ways, but if they are aligned with respect to each other, like this, bang, you see a triangle, which indicates that your visual cortex or your visual system is very much prone to recognize and bind aligned objects. And that means I have a feature here and a feature here, somewhere completely not nearby, but way across the visual field that is aligned. Basically, aligned means this is not a scalar relation, but this only really binds if both of these corners have the right orientation. Otherwise, it falls apart. Now, for that, a convolutional network is absolutely not designed. And so what is now important is to see the advent of visual transformers. Visual transformers essentially are a product of NLP, natural language processing, where the transformer, as such, not the visual one, has already been in use since 2017. There, essentially, every word is a vector. And these vectors, so these multi-component features, have to be put into relation to each other. So essentially now with the visual transformer, we will have the capability to look for features in an image that are not just scalar in nature, but may have a vectorial property like an orientation and other components maybe as well. And the way we go about it is as follows. We basically blow up an image into small patches. And every patch now, this is rather crude, but it works. Every patch is essentially seen as a feature and is encoded by a token. So essentially, let's say a little patch of 32 times 32 or 16 times 16 amounts to a large vector of features, especially if you have 3 channels of color. In this particular case, we end up with features of, 768 components that make up one patch. And on top of it, you basically then impose what's called a position encoding, a kind of a fingerprint that tells the network down the line at which position that patch has been located. Because once we're done with this, we just essentially have a big bag or list of tokens, pretty much like in text, but instead of having a one-dimensional position encoding, we have a two-dimensional position encoding. And this essentially gives us then what we call a token. So a list of values that cannot be encoded by just a single neuron, but needs to have a whole bunch of neurons, which, by the way, also happens to be the case in your brain, because there you can observe what's called microcolumns or mini-columns, structures of about 30 micrometers in diameter that make up your cortex and that contain of the order of, let's say, 100, 200 neurons that, work together as a unit. And they essentially are capable of handling vector kind of or tuple feature data. So once you have now these tuples or these capsules or tokens, the question is how to communicate. I mean, if you had a neural network, then every neuron communicated with its neighbor, at least in a CNN, via just a scalar signal on and off. When you have a whole vector, this becomes a bit more difficult. And the first hint or attempt in that direction already was taken in 27 by Geoffrey Hinton and others with the idea of a CapsNet, which, by the way, we also have in our Wolfram neural net repository. But I don't want to digress here. So CapsNet are way off. I want to look at how transformers, especially visual transformers, handle this. A visual transformer essentially has a kind of an attention mechanism to communicate or to handle the communication between all these different tokens. And it works as the following. This is a typical attention unit in a transformer, and it works as such. You have tokens and tokens coming in, and maybe of the order of a few hundred even, or thousands. And then in order to find out what token should talk to what token, what other token, and essentially end up in the output range, you basically create for every token a key, a query, and eventually a value. But let's look at keys and queries first. It's a little bit like a database where you have to have a keys and query in order to find anything. And here this is a mechanism where tokens find other tokens that they'd like to communicate with. So via neural net, I just create from the content of a token, who knows how, but that's what the network can learn, keys and queries. And then essentially these keys are used to say, well, what does this token provide? The query essentially encodes what this output token wants to obtain. And then we basically check what key fits into what log by, in this case, by, let's say, a dot product or by linear product or whatever fancy method you can think of, where you basically take this key represented by a vector and this query also by a vector where you see if these two match. The simplest method is a dot product. If the dot product is large, or if these are normalized vectors close to 1, then you have a perfect match. If it's 0 or even -1, then these don't fit. And so I basically do a dot product here. I normalize the whole thing by a softmax, and that gives me at the end an attention matrix, so an n times n matrix, that tells me what token should communicate with what other token. And essentially, then once I have this, I calculate from every token a value. That's a process running through this network. And then I essentially accumulate all these tokens at the output side of this network according to my attention matrix that I have formed here with the inner product and softmax. And once I have accumulated all the incoming tokens here at the output side, I have the chance to have one final process, a projection network that then produces the output. And having done that, I basically have now a beautiful mechanism for communicating information between the tokens. And that's exactly what in visual transformers happens. Here I have a visual transformer that basically looks as follows. First, I have a patch embedding, essentially a little network that takes incoming image and produces tokens, output tokens with their embedding. Here in this case, I have 7 times 7 tokens, so total 49 tokens going out, plus a class token, an additional token that I just put into the mix in order to extract it at the end and to read out the classification that this network has derived from the input image. Here is a position embedding, and then I go into the following list of virtual transformers with 50 tokens, and every token has 768 components. Okay, and this is how then one of these transformers looks like. This is exactly what I explained just a minute ago, and then usually in between you also have then a multi-layer, in this case a 2-layer perceptron to actually do some processing within one capsule. And well, at the end of the day, if I go back here quickly, I can see that in this particular case, the encoder has 12 of these visual transformer units. And once it's done, I read out the classifier token, just run it through a linear layer to basically end up with 1,000 classes, do my softmax, and then I can basically do all the image classifications that I used to be able to do via convolutional networks. And just to prove this, here, the transformer network applied to this image gives me the classification dog, which appears to be pretty much on target. Well, why do I explain you all this? Well, there's basically, it's a game changer, and that's what I'd like to convey here. And this game changer really also excels now in version 14. What are the benefits? Well, the benefits is, first of all, that the transformers, they cannot just handle image data or natural language processing data or audio data. Everything is just a token, and you don't put a lot of modality or data-specific knowledge into your network that's being learned. So transformers are basically data modality agnostic. It's good for audio, video, text, speech, and so forth. That means you can mix up these modalities. You can relate text to images, images to text, and so on. Secondly, the connectivity of among tokens is learned, really completely learned in visual transformers. You don't have this bias that is intrinsic in convolutional networks, that you first look just locally and then your receptive field grows slowly as you move along the depth of a convolutional network. So you can make connections between image features already at a low level. Furthermore, you can communicate not just with scalar values, but vectorial or high-dimensional values that can convey directions and so forth. And last but not least, a transformer has a built-in gating mechanism, because essentially this attention matrix where you decide what can you communicate with what also functions as a gate, because essentially it can block a certain degree of communications, can basically neglect whatever it considers unimportant for the task at hand. All right, so what does that entail? Well, it entails the following. If I have an image here like of a dog, I can also create another image, which just looks like a drawing. Essentially, all I do is a gradient filter here that basically looks for the contours in this image. And this drawing for us humans is completely sufficient to still recognize this image as the image of a dog. Now, if I run a transformer network on the original image, I get the classification beagle. And still, if I run it on the drawing, I still get, well, the classification of a dog, a bloodhound, which is, I guess, good enough because the color and the texture is gone. So it could be any kind of dog, strictly speaking. Now, what does that improve, or how does that improve compared to our ordinary convolutional networks? Well, that has the advantage that it doesn't go by textures anymore. It doesn't go by filter banks, which are perfectly okay to do the classification if you go via the image. But once the texture is gone, because you're just looking at the drawing, it goes way wrong. I mean, here in this particular case, you get the classification. It's a chalkboard. Well, strictly speaking, looking just at the texture of the image, it could be a drawing of a dog on a chalkboard. It's a legitimate conclusion, but of course, it basically doesn't see the drawing, just the outline. It just sees the texture. And this not only holds for one of our first neural networks that are already 10 more years old when it comes to image identification. Also, the more recent ones like EfficientNet have the same issue. They think it's a Walker Foxhound. And then when it comes to the drawing, they come up with something completely ludicrous, round worm that's completely off. All right, so you see the benefit of visual transformers lies in the fact that it can actually see the outline of an image. There are some drawbacks, though. The one drawback is that in order to communicate or to relate every token with every other token, you have an O(n) squared complexity, where n stands for the number of tokens you put into relation with each other. And that can be rather, it doesn't scale well, let's put it this way. That's why a lot of effort currently is being put into the endeavor of changing this complexity to something of n times n log n, n log n, or even just n. And one keyword maybe is Mamba in that respect, but that's still to come. So at least when it comes to Mathematica. Transformers require more training data, simply because all these attention matrices, the networking needs to be learned. You don't have that strong bias as you have in convolutional networks, and that's what requires just more data in order to avoid overfitting. And last but not least, the execution of transformers calculating keys and queries and values and so forth is a bit more demanding, and so you do need more computational power to run in these networks, not just for training, but for inference as well. Okie dokie. So, all right, so what does that entail? Well, let's first now look at segmentation in image processing. And there I do now one step back. I'll go back to good old convolutional networks, and one very potent one there is a U squared net, not U2, but U squared. If you want to look it up, it's a network that was developed in just 2 years ago in 2020 by people at the University of Alberta, Canada. And that network, if you look at it, is a typical U-shaped network, except here, unfortunately, the U is upside down. You basically process and go deeper with a higher and higher level features that you decode and then encode. And once you have the encoding, you can basically produce a segmentation mask. But not only that, you also encode here at every token here. You essentially have another U-net where you just look at not different scales, but different complexities as well. And this, double whopper when it comes to scale and complexity produces really good outputs. And especially this network has been trained on lots of data to distinguish foreground and background, saliency and non-saliency. So you can basically apply it to an image, like here, the image of a sailboat. And if we, whoops, sorry, it was not the sailboat. And if we then apply to the alpha channel, you get here the a mask essentially, and all the background is gone. So obviously we use that for a filter and the remove background command in Mathematica. So another example here, the saliency filter is basically running this neural network to figure out what in the image has high saliency. And then once you have that, you can easily apply this to remove the background in an image. And this works so well that you can also do that for video. So here we have a video of a bullfinch. Just 2 seconds as a demonstration, and this is even pre-calculated to just save a few seconds of processing time. And you see the background has been removed. So the first neural network here in this particular case that is readily available and applicable to to video data. All right, now that was still a CNN, a convolutional network, and now we try to reap the benefits of actually using visual transformers. And the most significant visual transformer package, a foundation network that has been published last year, is a so-called segment anything model by Meta, formerly known as Facebook, and they have come up with this publication in April of last year that has been, well, a visual transformer has been trained to segment images, and the training data was humongous, a very large data set. So this is, again, a so-called foundation network, a network that should be applicable pretty much to any image that you encounter. And we'll try it here. So we here have the image of a cat. I just define a rectangle to specify what I'd like to have segmented. So that is essentially here the region. And then I can remove background to say, well, whatever is outside regard as background and vice versa. And I get this output. So just the cat properly segmented. So this is an example of what's called semantic segmentation, because the segmentation doesn't go by color or texture or anything like that, but it recognizes the object and tries to segment one object at a time, which is usually what one wants and which can be rather frustrating if you try to do it by any other means. All right, just to demonstrate here this SAM, this segment anything model by Meta, comes in 3 sizes, small, medium, and large. And just to show you the size of this thing here, this is the part that patches or breaks up an image into patches for tokens, and this is the entire network, the encoding part, and it consists in this case of 32 layers of visual transformers, some of them working more locally, not on the entire image, but on the neighborhood to relate tokens. And then you have these global visual layers in between where every token gets related to every other token. And these networks are big. They're not just trained on large data sets, but they also have lots of basically parameters. And this particular one is 2.5 gigabit large. That's why usually you ask an API to do the segmentation, but we provide this network as a whole. The small one is around 300 megabytes, the medium one is 1.2 gigabyte, and the large one is 2.5 gigabyte in size. That only holds true for the encoder, because you first encode the image and then the second part comes separately and can be applied separately. You decode then that encoded image into a mask, and that whole structure is much smaller. I'm not going to look into it now. It only entails 20 megabyte of data, which of course is smaller, A, and runs faster, B. So you can encode an image once and then you can ask for all kinds of segments repeatedly, because the decoding, essentially the mask forming, is much faster. And last but not least, once again, the quality of the data that they have produced, 11 million images for training with 1.1 billion high quality segmentation masks that have been used to train this network. So this is what we now utilize. And just to show you how great this works, this is an example of a rather confusing image with lots of vegetables on a patio. And here is the resulting segmentation that is done by the medium-sized SAM network. And this is obtainable in Mathematica via the command image segmentation components. All right, and well, you can essentially extract, this is another overlay, just shows how well the segmentation is done. And then furthermore, you can basically request particular parts of an image to be segmented, where you can indicate segments by points like it's done here. So essentially here, I basically put points on every egg, and then I can get essentially a segmentation with all these egg segments. Or I can, as we have done before here, define a region of interest via a rectangle. This particular case, I just have booked here, targeted the zucchini, and then I segment that, and that's a segment or the mask for the zucchini. Okay. Well, I pointed out that you essentially have what's called a foundation network, which basically should be applicable to any kind of image you throw at it. So I just take an unusual image now, take a painting from a Toulouse-Lautrec, a French painter who has, well, painted here a soldier on a horse, and I'd like to segment the soldier. And of course, this is now something you may not expect to work as well, but as you'll see, it does. Here we basically define a rectangle that encodes the officer itself, and now I can run the segmentation, and I get the mask, and I can superimpose the mask on the image to basically extract the painting of the soldier itself. You may have noticed that I did not run these commands one by one. The reason for that is that it does take a little bit of time to run a 2.5 gigabyte network. Just to give you an idea how long it takes, I'll run this particular example explicitly, and here we go. So now I activate this, and you see that here the medium size encoder encodes the image. That's the tedious part. That takes, in this particular case, roughly, 15, 16 seconds. And once that's done, it basically just runs the decoder, and the decoder is much, much faster. And here we have the result. Just to give you an idea that now, because it's a visual transformer, the entire endeavor is a little slower than we are used to. All right, so there are a few spin-offs with these segmentation capabilities. One relates to image contents. So if I basically look at the contents of an image, I can now not just get the elephant and the bounding box, I can also get a mask, and a masked image, essentially a cutout piece of what I have detected here. In this particular case, there are several animals in this image, elephants and zebras, and they are being classified and extracted. Or in this particular case down here, I can ask, for example, a masked image for all the image cases, which then gives me the tag of what I have found, and not just the bounding box, but essentially the extracted segment of the cat in the image. One more spin-off, image paint. In paint, so far, if you had an image and you were interested in deleting a certain part of an image, in this particular case, a duck, I think, a duck or goose, I think it's a duck. Here in this position, I would have had to generate essentially a marker image. A marker image that basically tells me what part of the image I'd like to delete. Now, that has been rather tedious, so now you can think of what happens. You can just use a point and use that point to indicate the duck, and internally we basically just run SAM and segment this part of the image and then delete it for you. So you're released from having to create a marker image yourself. And that whole story also works, by the way, for a rectangle. You just specify what you like to have deleted, and here you go. All right, image synthesis. That's now a feature that we have that is based on a service, outside service, because it's currently very demanding, and these networks are rather large. I guess we will have in-house solutions down the road, but for now, it's a service, in this particular case, a service that we obtain via OpenAI. And here we just can call upon this service via image synthesis. I provide just a sentence of what I want, in this case, a painting of a ram in the style of Monet. And if I run this, I get this output, or as an example, I get this output. I always get something else. It's not a deterministic process. And well, I guess it's definitely a painting of a ram. If it's Monet, it gets close. And here's a few other examples. So basically, I want to have a drawing or a ship. Essentially, I want to have a representation of a ship, but I specify the different kinds of representations. A kit drawing, here a vintage photo, or a detailed kind of technical diagram of a ship. And this is what I got back. So kit drawing, a ship that looks like being taken on an old photograph, or just a technical drawing of a ship. And you can see, for example, if I rerun this here, you see how a service is working. So I run image synthesis. This connects me to OpenAI. It takes a few seconds to obtain the result. And once I get the result, I get a new kit drawing of a ship. Here we go. Okay, now having this capability, you can now, of course, come up with a question, well, isn't that a great way to do in-painting? And sure it is. Well, I would even call it X-painting, but because this is a good way to in-paint large section of an image that you didn't have before. In-paint, as far as we have marketed so far, was good to fill in small portions of an image, not large portions. But you can basically dream up large portions of an image. Here we have an image of two puppies. I essentially can go ahead and use my image segmentation filter to obtain a mask that just cuts out one puppy, or essentially the surrounding of one puppy. And then I can say for image synthesis, well, I'd like to have this puppy in the middle of a dense jungle. So keep that image defined by this mask and just come up with a solution. And what I get here is this output. So essentially a fairly good imagination of a little puppy somewhere in the Amazon jungle. All right, just to complete the picture, this is not a built-in command, but a network we have available via our net repository. It is a network taken from this particular section in our WolframU net repository, and there you can also then get all the sightings and the original paper where it was taken from. And this network basically was trained, again, a visual transformer, not just visual, but a transformer to handle text and images and to relate text and images. And this basically allows you now to take an image in and to get the text out. So basically have a caption of a text. And just to show you what's possible, first of all, the function that I'm using here are defined below. So if you're interested, you can have a look at it. And then I can just look what this has produced. This basically came up with the caption, a white dog with pink heart-shaped glasses. And all of this is a photo, which exactly is on target. Couldn't have done it any better. And here another vintage photo, the one that we just generated. This says, okay, this looks like an old brick in the bay of the city of St. Petersburg, Russia. It's a stock photo. Well, here we can see the problem of hallucination. The old brick is perfectly okay. Bay is maybe also okay because you can envision that this is a strip of land in the background, but the rest is completely dreamt up. It could be St. Petersburg. It's pretty flat in the back, but you're definitely missing, let's say, the castle, the fortress of St. Peter St. Paul, or any indication that this is taken in the region of St. Petersburg, Russia. So be aware, this is not completely foolproof. All right, so let's switch over from images to video. And as I've promised, we have new ways to generate videos. In particular, we have now ways to use a 3D graphic object in Mathematica and basically, create a flyby, a video that basically depicts a flyby for this object. So as an object, I have taken here the result of a 3D cellular automaton. So that's a state of a 3D cellular automaton at a certain given point of time. And here I basically define a path through this construct. First, I basically define all the points that I'd like to visit. Then here I define a path, interpolating function that goes through all these points. And once I have defined that, I can just basically define a function that walks along that path, that defines the viewing angle, the camera position, and then, of course, also where you're looking at. This is basically just taking the function and adding, essentially projecting a tangent into the future of the path to basically look straight ahead. All right, and then once I have that, I can use parallelize and so forth to just run it, just to cheat a bit to save a few seconds of processing time. And you obtain essentially this kind of video that is a kind of flyby or fly through this 3D object. And as you can imagine, you can generate all kinds of pretty neat videos that way. Okay, once you have a video, then of course, editing it is always of interest. So we have here commands video join and video, other video commands I get to in a second. With join, we now have the capability of not just concatenating two videos, but to also generate a transition We have here three forms of transition with a certain overlap. One is fade, where basically you have first the first video and then slowly you basically fade into the second video by changing the alpha channel of the first and second video. And this is one transition. The other one is a push transition, basically where you physically push from one side the other video out of the frame. And the third option is a wipe. Essentially, you just wipe the content of one video over the other one, and this gives this effect in transition. All right, and all this code is simply generating two of these videos and then depicting these transitions. Okay, then once you have a video, you may want to combine more than one track or audio or subtitles, and this is what I do here. Here I have an audio that I get from my example data set. Then I have here a video combine where I took the video that I just created the slide before. I take the audio and I generate here some subtitles, and this gives me then this particular video. Okay, this is the video with the sound, and if you want to see the subtitles, you have to go down here. Say I'd like to have the subtitles as well. All right, here we go. So you get the idea. And then, of course, the inverse is to have such a video and to extract subtitles, to extract audio, or just to extract the video track itself. Okay, so that allows you more editing, and then just a minor update when it comes to video overlay. Here we have just a video that I can load, and then I can overlay anything on top of this video, and I can make this time specific. So I can define here a time interval from time to second, well, 2 seconds to 6 seconds. Please play here this or place this icon on top of the video, essentially here at the center position. And the result I get after a few seconds of processing is the following. Oops. And yeah, well, can put a watermark here or any icon, whatever you like. Okay, so these were some editing features, and now some video rendering. Candy. As you may have seen beforehand, we now have the capability of putting textures not just on polygons, but on any kind of object, also like a sphere, a cylinder, and the like. And that not only holds true for images, but also for video. So this is a video, so-called 360 video, taken from Wikimedia. This has been generated by NASA, the Goddard Space Flight Center, and it basically depicts a little plane flying across a glacier in Alaska. So I think you get the idea. This is pretty much like a world map. It's a 2D video, but basically can be mapped onto a sphere. And it has a nice ratio here of 180 degrees times 360 degrees. So it has a 1:2 aspect ratio. So if I define this as a video stream and basically say, well, take this video stream as my texture, make it dynamic so it does update, and do a spherical projection onto a sphere, then I can basically view it on a sphere. But here I do one more little trick. I basically place my viewpoint in the center of that sphere. And that basically gives me kind of a 360 surround video where I can basically look around, look up, look down, any which way I want. And at the same time, I can hear, that was programmed explicitly, a button to start the video stream, to pause it, and to stop it. I can start the video stream and then essentially watch a movie, and while watching it I can change my viewpoint. So I can look up, I can look down onto all the icebergs, and I can look in the rear of the plane, and I can look up front again if I want to. All right, so I guess you get the idea and the possibilities that this opens up. Okay, let's tackle the section about audio, and in particular speech. speech recognition, and speech synthesis. Well, that is not completely new. We had that before. So if you were to give Mathematica a small audio file like this one here,
Right then. Perfect timing.
you can run it and it automatically then uses the operating system to convert this into text. But not only that is possible, now you can also utilize more refined providers like OpenAI and Google Speech to do the transformation from audio to text if you want to. In essence, in this particular case, you don't get anything different. You simply get here the sentence right then, perfect timing. But we can just give it a try. Let's do an audio capture here and let's see if that really works. 1, 2, 15, 23. So let's see if these numbers have been recorded correctly. And here we go, 1, 2, 15, and 23. All right, so that seems to work. Let's just move on. For the inverse functionality, that is speech synthesis. Speech synthesis can take any kind of string or, for that matter, code that's then being read out to you with arbitrary voice of your liking. Well, in the case of the built-in version, the local method, nothing has changed.
A graphic consisting of a disk.
That's still the same, but now you can utilize also service providers like Google Speech, 11 Labs, and the like with more refined audio output.
A graphic consisting of a disk.
Or here, 11 Labs.
A graphic consisting of a disk.
So on top of it, you can, of course, choose the gender of the speaker, the native language, and then different narrators and different speakers with given names, starting with A with Adam, and then ending with T like Thomas. And if you want to have a whole list of possible speakers when it comes to 11 Labs, for example, here is a list of what's available for the English language. Okay, so I think that's straightforward. Let's put these two functionalities to use by building a small, you may call it Siri or Alexa for Wolfram Alpha. What you see here is a dynamic module. The dynamic module essentially provides buttons. The buttons start a recording that then saves what you have said in audio S. That's being converted via speech recognized to a string. The string is fed to Wolfram Alpha, which comes back with an answer. The answer is converted to an audio, to speech, and that speech is then being rendered via audio play. All right, let's give it a try. Let's record a question. When is the next total eclipse of the sun? All right, so we have here speech processing to recognize what I just said. This is the question I posed.
The next total solar eclipse will be Monday, April 8th, 2024, and the path of totality will pass through the United States, Mexico, and Canada.
Well, for such a snippet of code, not a bad result at all. All right, so let's move on to the remaining topic, and that is audio effects. In essence, we have here two commands that we have upgraded quite reasonably. So the results that you get have a much higher quality, and that is audio pitch for one. And audio pitch has the following effect. It basically takes the bass frequency of a sentence or a melody and can shift it up or down depending on the second argument, what you provide here as a multiplication factor. So let's just take a piece of music here from Franz Liszt, Hungarian Rhapsody. I think you get the idea, and now we can just transpose it to move up a little bit. Well, you've seen the entire pitch has been risen up by a factor of 1.5. And here I can just do the opposite, play the whole melody at a lower tune. Okay, so much for that. Just for some visual feedback, also did here an audio local measurement of the fundamental frequency. And you can see here, this was the initial tune. Here, this is the one where the pitch has been shifted upward. And this is the one where the pitch has been shifted downward. All right, so that's just the pitch. We haven't played the music piece at any different speed, which would have been a kind of a cheap way out. No, it has been just risen when it comes to the frequency or lowered. When it comes to changing the rendering speed of an audio file, you use audio times stretch, and that allows you to stretch or to shorten a piece of music. If you have a factor of 0.5, you essentially speed up the rendering. And this then ends up to be this audio. So in essence, if you want to play something really fast, that's one possibility to do it. All right, so just again, visual feedback. This was original music. And here you have basically squeezed everything into half the time. All right. So much for that. Well, thanks for sticking with me all this time to the very end. Tack så mycket, dankjewel, cc, arigato. I hope to see you again sometime soon, and please don't hesitate to ask a question via the available channels. Thank you. There's one open question right now from James Linton. He asks if there is also a way to analyze all the frequency, not just the fundamental frequency, in an audio patch, and I believe so. Let me quickly see. Audio. Gosh, I haven't done audio for a long time, so please bear with me.
Audio local measurements.
Right, and so what we can go for are here fundamental frequency, formants, higher frequency content. Essentially, what you may be interested in essentially are the mel frequency Zepf coefficients. Essentially, let's see if we can jump to that. Next. Here we go. So this is a kind of a heat map of time in the horizontal and the frequencies in the vertical direction. However, this usually is then a logarithmic scale, so you're not having every single frequency being depicted here, but you have bins of frequencies, and this gives you then an impression of how the frequencies are developed. Other than that, you can of course always take a patch or a little strip of audio and just run it through Fourier transformation, and just for that particular instant in time or interval in time, you can just do a Fourier analysis and plot that Fourier transformation. Okay, I'm seeking a method to incorporate the conditional expressions into a parametric. Okay, 15 is not related. That has been answered. Essentially, you have to use piecewise as a construct to have piecewise defined functions.
Okay.
And yeah, I think that that does not relate to audio as such. Was that in a program? Well, that's a good question. Essentially, Mathematica is a programming language, and the answer most likely is yes. I'm not quite sure what was that refers to, but let's see. All right, next question by Matteo. I have a .wav file, so a sound file, that has DTMF signals in it. How can I get to the tones or frequencies? Well, a .wav file can just be imported in Mathematica. So let's just go and look at WAV. Import export, and here basically it's one of the many formats that we support, and they just basically say import that particular file, and then You can instantly play it as an audio file, or you can use any of the other possibilities to visualize audio or audio formats in Mathematica. Shadi, do you have any idea how to visualize now sound quickly? Well, one was the male spectrogram that I just showed, and you can have also, well, this holds true for any audio. You can do an audio plot so that you can get the amplitudes readily available.
Or the spectrogram itself. And then the question is asking for dual tone signals, and it's basically the same question as you answered before. We would need to understand or find two main frequencies that are present in that signal.
Not spec. Gosh, what am I doing wrong here? Spectrogram. Why is it not?
Trogram, TRO.
TRO, spectro. Okay. Gosh. Okay, so spectrogram. Here we go. Essentially, you just put in the list of data or the audio itself, and then I can just pull up here the ref page and give you an example. So if I have an audio here, let's play it. So I'm not sure if you can hear it. That essentially was the tweaking of a bullfinch. And then if you play it as a spectrogram, then you essentially get this output. Again, time over frequency.
You might want to increase the magnification just a little bit to see some of that. Thank you. Excellent.
Okay, next question. How to apply some functions to raw data of an audio file that is to a single data to the single data points. Okay, so essentially an audio file is essentially just a list of, or several lists of real numbers, and any function in Mathematica can just be applied to such an object. So for example, let's take this construct here. So I could just try, and now let's try just to take, let's just, what function
audio
shall
data,
we take?
maybe?
Pardon me?
Audio data. I was wondering
Audio
if the question
data.
is, how do we extract data out of
so
an
here
audio
we
object?
have the data, and then you can apply any function to it. You can maybe apply the logistic, what do we have? Logistic sigmoid function to it, just as an example. That basically makes sure you don't exceed -1 and 1, which is probably lame in this particular case. So let's multiply this by 5 and then apply the logistic sigmoid. And then you get a new data set with all these values, and then you can just say, okay, I want to have an audio of this again, and then play it.
And as you were hinting on to begin with this answer, there are so many functions that already work on audio objects directly. But if there is anything that doesn't work, or there is a special operation, we can take the data out basically and process it in any way.
And just looking at that question list again, there's somebody looking for clarification that all this functionality that you've been showing here today, Marcus, is indeed built into the Wolfram language. It's not additional video editing software that you're using. So just to clarify that, this is absolutely all in the Wolfram language and built-in functionality with our image processing, video computation capabilities.
Yeah, you can do your finance, your protein folding, your image processing, anything in this language.